but I couldn't hear it. And so I carried on with class, and then some of the students said, "What is that sound?" I said, What are you talking about?" And then I realized that I had turned it off, but it was playing at a frequency that the students could hear, but I could not. Which leads to probably one of the pettiest things I've done. There were a bunch of students right outside my door waiting to get into the class across the way. These were high school students. They were just being high school students. But I was in a bad mood, or for whatever reason, I was annoyed. So I crank it up to a frequency I can't hear, crank up the volume, because I still can't hear it, and just start playing it. I shouldn't, but I did. Let's take it up to 20,000. Hearing test, there we go. It's about 4,000 hertz. 5,000. 6. All right. I'm out. It's about 12,000. I'm back. And I'm out again. We're at 18,000. 19,000. And then it stops. So of the younger folk, Kyle, you were the first one out. It's a personal question. Feel free not to answer it if you don't want to. How old are you?
I'm 24.
Anyone else besides Roberto and me older than that? Okay. Okay.
Well, I can tell you why my hearing is so bad. I've been around race cars. So
Okay.
like my ears are already shot.
Oh. We had a Subaru, a really mediocre vehicle. It's not playing. No one can hear it, right?
It is playing. No,
It
it is not.
And there was a hum in the back speaker, and so we took it in several times, and eventually I said, "There's a hum in the back speaker, why I can still hear it." Well, the guy said, "Well, the guy checking it has been around a lot of machinery, so he's not really hearing that stuff." And I'm going, "Why did you put him on that job? It's not like it's a surprise." What the problem was. They eventually ordered a new one, but ordered the wrong one. I was so ticked off in class, I railed on this guy named Danny. And then a student, and kudos to her for doing it, said, "Danny, you mean my cousin Danny?" I'm thinking, oh crap, I just badmouthed him.
I got a funny story. So when you're letting the race car warm up, there's of course it's like all aluminum, so you have to let it warm up before you have it. And I had earplugs in, and none of the other guys had earplugs in. And I could hear, like, I felt the vibration. Like, you can't really, so when you get around the other noises, the earplugs cancel out. You can hear the stuff vibrating actually in the motor.
Mm-hmm.
I'm like, cut the motor off, cut the motor off. It's getting ready to blow up. They're like, no, it's fine. Next thing I know, they hear a pop. It blows up. Just sitting there warming up.
Were you hailed as a genius?
Yeah.
All right.
I was like, if you wouldn't listen to me the first time, I would have saved the motor. But
Did you tell them the secret, or did you just maintain your air of brilliance?
well, I told them, I'm like, that's why you have earplugs on when things warming up.
All right, so next step, as we're doing it, I don't know if you noticed, one of the reasons I swing it vertically like this is I want to avoid sound sort of coming towards you and away from you. I think, now I don't hear this because, not because of bad hearing, but because I'm at the center of it, and this end of the tube is basically traveling the same speed relative to me the entire time. But to you, at some point, it's going towards you and away from you. So do you hear a difference in this and this?
Very, very faintly.
Well, you basically have a Doppler thing going on where it's going towards you and away from you. So let's talk a little bit about Doppler. And the remote, there it is. And I usually do absolutely spectacular drawing on the board with circles that I have to pretend are circles and things like that. But we can actually do better now. And blinking means something there. We'll pretend that's about to come on. There we go. And just as a side note, Danny was not her cousin. She was just messing with me. All right. Sort that down. Zero. All right, so we have something giving off a source of sound. Let's darken the room slightly. With the other one. And so, if you picture each of these as the peak of a wave, and let's see if we can freeze frame it. So the wave coming off of here is the same wavelength as here. Speed of sound is the speed of sound. We assume it's not varying much between the two, the source and the observer. And so the frequency that's emitted should be the frequency that's observed. Or the rate at which the sounds are released are the same rate at which the sound is observed. So we have a source frequency and a perceived frequency that are the same amount. If instead we give them some speed, so now the source is heading towards him. The peak-to-peak distance is dropped, and so therefore the frequency is increasing. Now the frequency that the source is giving off hasn't changed. But the frequency that the observer will hear has changed. And then they crash. Now on the backside, the frequency should drop because the wavelength has increased, which is inversely proportional to the frequency. Now, where have you experienced this in real life?
Sirens. Sirens?
Okay.
Air show.
So you've done air show before. Have you heard the sonic boom yet? Have you heard the sonic boom? I know sometimes in air shows in Fort Jackson in South Carolina, or Charlotte Air Force Base, they would get permission to break the sound barrier. And sometimes there'd be just some young pilot who just wants to show off and then gets in huge trouble for doing it. So anyway, the sonic boom.
I don't think so.
Okay. So obviously there's a difference and what is observed and what is emitted. Let's put that back at 0. There we go. And let's have the observer move now. So it's still being given off the same, but the observer, since it's traveling this way, are going to be hitting the wavelengths more frequently, and therefore we'll hear a higher frequency. And then once on the other side, moving away, it's going to be a lower frequency. And then, let's put the observer at 0 again. And let's put the source slightly faster than the speed of sound. You start to get this cone build up here. Remember that each of these lines here represents a high pressure, or a higher pressure. You now have high pressure right on top of high pressure. And so what you're getting is this doubling, tripling, quadrupling. Generally you're giving off frequencies. If you're giving off 343 waves per second, or oscillations per second, your brain doesn't have a chance to process one before the next one hits, and so this just comes across as incredibly loud. Also with high pressure, you should feel the vibrations, assuming that's an aircraft. If I increase the speed, notice what happens to the cone. You get a narrower cone. So the faster the source is going, the narrower this cone is going to be. Even though it looks more spread out than the last one did, again, picture a lot more cycles per second than what's actually being shown here, and you get, well, basically even louder. Mythbusters did something on being able to break glass with the sonic boom. And they basically ended up flying a jet, what seemed like really close to the cabin where they had glass stuff in it. You've seen it, I guess? So, what I want to do then, of course, is derive this formula. At least for the subsonic speeds. The fan were quieter, I would leave it on because there's some other stuff I want to hit later. Or maybe I will leave it on because. There we go. So I have a source here. I'm going to label it E for emitter. So I have an emitter. And I have my observer. I'm just going to use R for receiver. So he's going to emit a sound. So he's going to be moving to the right at some speed V. Let V sub S be the speed of sound. And he's emitting at some frequency S sub E with a period of T sub E. They're reciprocals of one another. So he emits the first wave, and in the time of T some E. That wave has traveled out to, let's just say here. So this is basically the distance the wave has traveled. In one period. And then he gives off the second wave. So the wavelength that is going to be observed is basically this distance right there. Because once that second wave is emitted, how fast the observer is going is absolutely irrelevant. Because once that sound is released into the air, it is only dependent upon the speed of sound in that air. So to find that wavelength, the wavelength would be how far the speed of sound went, minus how fast the observer went. Or the emitter went. I guess I just labeled it as V. So Vs minus V times d sub E. That is the wavelength that will be observed by the receiver. So that's lambda sub R. Well, I know from V is equal to F lambda that the wavelength is equal to the speed of, that's the speed of sound divided by the frequency. And so this right here should be the speed of sound divided by the frequency that is going to be heard by the receiver. The period from the emitter is just the reciprocal of the frequency. So this is Vs minus V over the frequency of the emitter is equal to Vs over F sub R. Solving for F sub R here, the frequency that the receiver will sense is the frequency that's emitted times the speed of sound over the speed of sound minus the speed of the source or the emitter. I am going to put that subscript E there. Speed of the emitter. And so that's basically half the Doppler effect right there. We can then do, let's go to the classic. If the emitter is blowing a horn at 440 hertz and driving toward the receiver or observer at 30 meters per second, what is the frequency that the receiver is going to get, or the observer? What frequency will be observed? Well, come straight plug and chug. This is 440 hertz times speed of sound, which we'll stick at 340 meters per second, over 340 meters per second minus 30 meters per second, which is 440 hertz times 340 over 310.
$482.58.
482?
Yes.
0.58. So you hear a higher frequency as expected. When the car comes towards you and with the horn honking, you hear it at a higher frequency. When it passes, it should drop. So what changes in our equation when the car passes the person is now going away from them.
You add the speed of sound and the velocity of the emitter.
You said add?
Yeah.
Yeah, and this becomes plus. So when he's going away, this will be 440 times 340 over 370. So this is toward and away. What is it again? 404. 32. Thus a higher frequency to the lower frequency as it passes. Now there is a certain amount of, this assumes that it's heading straight for the person and going straight away from the person. Now in reality, we don't experience that. Very rarely do we have a car coming straight at us and then pass through us. So the fact that there's a transition there happens because the car is not directly on us. And it's a matter of geometry. It's generally not presented in, actually I don't think I've ever seen it presented. It's within the realm of math, but we're going to skip over if it's off to the side as it passes. Now, if instead of, questions to hear?
Couldn't you just say it's like the velocity of the emitter, since it's instead of like plus or minus?
Typically done by speed, and you put a plus or minus in there. I guess if we were doing, one reason why not to do velocities is if that's velocity, then all of these have to be velocity. And now we're dealing with division of vectors, which I've never actually seen legit formally laid out. So it's generally presented as speed. Generally talk about the speed of sound, not the velocity of sound, since it basically goes everywhere.
The opposite of toward, what is in English? The opposite of toward,
Away?
away.
Yep. Or for those who've been exposed to other ones, toward or towards, throw an S on the end, it's perfectly legitimate. So typically written with a plus or minus, and I've seen complex charts, and frankly it comes down to, you can hear a higher frequency or lower frequency, and then use the sign that's going to give you what you need. I know it's coming towards me, it's a higher frequency, so I'm going to subtract in the denominator. Do note that speed of the receiver was 0 meters per second. And so we need to account for the receiver moving. Other questions before I erase stuff?
It shouldn't be exactly the same, how you say that, relative speed, just one is plus and the other one minus. Sometimes, let's say, if this is standing still, let's say the receiver, then this is coming at 340. That's a relative between them, no?
Right.
And we went past, it's still 340.
Are you making an argument for this would not change at all? If
It's,
the observer moves?
I know the just design will change, no?
No, if the observer or the receiver moves, then it is different. Because the difference is dealing with the speed of sound. That the speed of sound is, we're gonna pretend constant. Yes, it can vary, but the speed of sound basically is, once it's released, the speed of the wave is not dependent upon either of them. But if the observer is moving, it's as if the speed of sound is faster. And so what that ends up doing is affecting the numerator. The denominator is affected by whether the emitter or the source is moving. The numerator is affected by whether the observer is moving. Did I miss completely what you were trying to say?
You know, I know by experience that the frequency change, that's obvious, no? The train or the car is approaching to you, is high pitch and then it's low
Right.
pitch. But I just was thinking in the formula. No?
So you're just taking in the formality of it? Is that?
I just trying to analyze it, no? That, this speed of the. Yeah, it looks good, everything looks good.
Let's change this around. So now let's have this at rest, the emitter at rest, giving off sound. There's some wavelength that's emitted with some particular frequency and some period. But the observer or the receiver is now moving. And so the question is, how much time does it take for the observer to hit two peaks in the waves? So we'll just let time is equal to 0 when that first hits the first wave as he's traveling to the left at some speed v. I'm going to call it v sub r. Now while he is traveling to the left, this wave is coming at him to the right. So the period that the receiver is figuring out, he's going to be traveling some speed v sub r times the time t sub r, while the wave is traveling to the right at v sub f t sub r. Draw that the other direction. Because you get that first wave, and then one period later, you're hitting the second wave, the received period. And this total distance should be the wavelength that's emitted. Did I mess up there? Give me a second here. Let's travel in this way. Because that's where at that point. That is the wavelength. Yeah, that's right. So the wavelength that's emitted is equal to VSTR plus VRTR. or VS plus VR, times the received period, or the observed period. This is the wavelength, which we've talked about before. That's going to be the speed of sound divided by the frequency of the emitter. And that's equal to the speed of sound plus the speed of the receiver divided by the frequency observed by the receiver. And so the frequency of the receiver becomes VS plus VR over VS times the frequency that's emitted. So if the emitted frequency is 440 hertz, if the receiver, the observer, is heading towards the sound at 30 meters per second, then he will hear 440 hertz times 370 over 340.
$478.82.
Now, when the car was coming towards the person at 30 meters per second, the person heard 482.58 hertz. But if the car stayed still and the person went towards him at the same speed, there is a difference in what is perceived. Officially. Now, whether the person can tell the difference in those 4 hertz, that's a different story. And so we end up with the same situation of if the receiver runs away, so this is towards, and then away, instead of plus, you're subtracting. So it becomes 310 over 340, that's 440.
$401.18.